let me introduce you guys. Go to the next slide if you don't mind, Alan. So Alan Ambler works, just go back one if you don't mind.
Uh-huh.
Ambler works with us at the Alliance. He also has his own practice. He's the former head of the AWWA Water Main Rehab Committee, and he's done more pipe bursting of AC pipe in the U.S. than anybody else. And Alan, what do you have, over 50 miles under design by now?
Yeah, close to that, 42 in the ground, another four getting ready to be put in the ground as we speak. They've started the project, and then that's just direct design as the EOR for it. I'm sure there's a lot more that I've helped over the years. So
Good for you. Well, we're delighted to have you here, Alan, and
thank
also
you.
Matt Hahn, technical service engineer with Performance Pipe. Matt, tell us a little bit about yourself.
Howdy. Yep. So I'm a technical service engineer with Performance Pipe. If you're not aware of Performance Pipe, we're one of the largest manufacturers of polyethylene in North America, polyethylene pipe, sorry. And I've been with them for about 6 years. And my day-to-day job is basically answering questions from people on how to spec in, design with, install, and repair polyethylene piping. So that it's kind of why I'm glad to be here to help give my input.
Yeah, well, we're glad you're here too. And Matt's been a regular speaker here for us at whether it's PE Showcase or the webinar program. Both these guys are great resources for you in the audience. And next slide, please, Alan. So I'm announcing today that my sidekick for many years, Drew Mueller, has moved on to ISCO Industries. Hated to see him leave. What a great talent Drew has been over the years, a great speaker and a wonderful expert and knowledgeable guy about all things polyethylene. So he will be missed. And any technical responsibilities that he's had are, now on my and Dan Landy's shoulders. And the next slide, please, Alan. So any problems today are now Dan Landy's fault, not mine. So Dan Landy, we welcome you to the webinar program.
Yeah, you know what they say, it runs downhill, and I'm at the bottom of the hill now, so looking forward to it.
So we'll give you Dan's email address at the end. Questions, CEUs are going to Dan. He's our spec expert now. Very, very excited to have him. So with that, Alan Ambler, I'll go video off and turn it over to you two guys. Thank you very much for being here today, everyone.
All right. We really appreciate you, Pete and Dan. Thank you for being at that bottom of the hill, pushing everybody upward as we go through there. So the email, just to fast forward to the end, is dlandy, Landy, at pepipe.org. Of course, you can get Pete at DYKE at pepipe.org, or myself at Ambler, AMBLER, at pepipe.org. So this is an overview of what we're going to be talking about. So we're looking at HDPE testing from the field and inspection view. So these are the things that we could be looking for as a construction observer out in the field when we're trying to ensure that the materials and workmanship are conducted in the best manner possible. So we will talk about electrofusion fittings, which you're seeing right here, an appropriate preparation of that fitting prior to performing the electrofusion. Then we'll also talk about leak testing on the pipe. Of course, if you've attended any of the webinars previously, we are a leak-free system from point A to point B. If it is monolithic throughout the whole run, so there are no joints that leak when fused properly. And so we'll talk about what's unique to high-density polyethylene in that aspect to make sure that there are no leaks and the system is operating exactly the way we need to. Installation inspection. So whatever your method of installation, whether or not that be open cut excavation, pipe bursting, horizontal directional drill, there are items in order to be able to be aware that are specific to high density polyethylene pipe, as well as general construction observations in particular that we'll go over there and to make sure that you're aware of before your next construction observation process. Fusion qualification and then manufacturing QA/QC. Matt Hahn has done this presentation before with the manufacturing QA/QC, really first and foremost in the forefront. That was last year's version. What that tells me prior to being a civil engineer that works with this process in the field and want to make sure that it is constructed correctly, is just the sheer rigors of testing that that Matt Hahn and Performance Pipe and all of the other pipe manufacturers and parts manufacturers and equipment manufacturers have to go through in order to be able to make sure that you have the highest quality part and piece and equipment to even begin with before we get out in the field. So we'll close some of that. That is essential to be able to make sure that you know, as a civil engineer, that what you're putting in the field is the best possible quality that we could imagine. So receiving pre-construction inspection, we want to make sure that when we receive this pipe material, it is free of defects and other manufacturing problems. We want to stack it correctly, and we want to make sure it's transported correctly. So we're looking at a larger diameter, which poses different problems. Obviously, you've got a semi here with only 2 sticks of pipe on it. If you need to pull together a 5,000 linear foot 48-inch job, that's going to be a long haul to be able to get you lots of pipe material. There's other ways to do it depending upon your project location. Sometimes they can float the pipe and then direct barge it directly to your project site. Lots of different ways to be able to make sure that this gets to you safely. We want to also make sure that it's transported or moved while it is in the storage yard well. So if you're using a forklift, we want to check that for jagged ends or burrs, have the widest possible spread on that forklift. So that way you're holding girth of that pipe material fairly well, so it's not lopping off from one side or the other. Typically in pipe or any type of long installation process, which a completely fused system will allow you to take advantage of longer lengths, a lay down yard may be long and longitudinal as opposed to a kind of square and rectangular where you would stack up pipe for a segmental installation. So in instances where we have that long and longitudinal laydown area, there are productivity tools that make it so one worker, one employee can fuse up very long runs of pipe to be installed all at once. That's one of the true benefits of the trenchless technology, coupled with high density polyethylene, which allows us to be able to install long runs all at once. So these are just a couple of images showing you how to move this equipment and be safe with it. Again, we don't want to denigrate the pipe as we're moving it about the project site. So,
I always like to point out when we're talking about transporting and receiving pipe, that this is one of the key points where pipe can become a hazard. It can become a hazard to itself. It can be a hazard to personnel interacting with it and to the project. So when I say pipe can become a hazard to itself, say you've got over deflection, you can have damage from mishandling. You can extend your installation times because you're trying to repair damage. As far as personnel interacting with it, so obviously it presents a hazard to other transporters of the product, to pedestrians that other people transporting on the roadways as you're trying to deliver it to a customer, or to pedestrians. It's also, if it's improperly handled or stored or packed on a truck, it can be unsafe to unload because of stored energy. You've got heavy pipe, especially in these larger diameters, at an elevated position. So you've got potential from gravity. Then also, if you're talking about coiled products, you got to be aware of the safety concerns when you're dealing with unmanaging those coils for installation. And then the other bit is you can damage the project. So you don't want delays because you get the wrong pipe delivered, or you've got to reround the pipe a whole bunch because it wasn't stored properly. Those are the things that I like to point out when we're talking about transporting and receiving.
Great. And what are we looking for when we're inspecting for receiving and pre-construction inspection?
So obviously what we're looking at most of the time for when you receive a product is the paperwork that you receive. So there's and markings that may be on the product. And so what's the point of that? It's in order to get you received what was ordered and that it's a product that's suitable for the application. So usually when you receive a delivery, it's going to come with a certificate of quality or conformance. So you'll see the customer name, the order number, the date of manufacture, the material type, any QA testing results if they're requested, and then also, but most importantly, the standards that that pipe was manufactured to. And so why is that important? Because when you look at the print line that would be actually on the product, you're going to want to make sure that those details line up. You know, those could be the manufacturer, they can be the size and DR of the pipe, the material that it's made of, that it's high density PE 4710 material, and any other standards that may be applicable, whether it's a sizing standard like F714, which is very common, or that it's manufactured to AWWA requirements for potable water applications. So C906 is common for 4-inch to 65-inch. C901 would be your smaller service sizes. But that print line also correlates with the traceability that the plant should be able to provide, indicating any other certifications or dates that this product was manufactured or tested.
So speaking, fellas, of damage during transit, I got a great question about, is there a way to quantify the damage by chips or visual damage to the exterior of the pipe resulting from transportation?
Now, I would say quantifying it. So we will talk a little bit in a few slides, I think, actually, about the industry standard is 10% of the pipe wall would be allowable damage. So it may be difficult in some cases of damage that you may see to quantify that, the effect on the wall, but that has been the industry standard for going on 50 years.
So what I like to say, because the product is so workable in the field, and if we have a long run that's already been fused up and something happens during transportation of the run to along the job site, then the crew obviously is responsible for that, as opposed to transportation along trucking routes or what have you. But that 10%, there are feeler gauges that will allow you to be able to go into the gouge, more so that'll give you an accurate record on it. But what I like to say is, when in doubt, cut it out. So the product is so durable and workable in the field that the actual process of fusing after you've cut a section out, depending on the pipe size, is something that doesn't stop or denigrate the actual product itself. So that joint that we're replacing a cut section with is as strong, or if not stronger, than the actual pipeline itself. Later on, we'll have good examples of scrapes and then also gouges, so that way you could see the visual. And I'm extremely grateful that you guys are already asking these wonderful questions, because it is covered and it is important for you to be able to keep track of.
If you hit next slide, I believe there is a
Mhm.
picture. Yep.
Yep.
Yeah. And so this is a great example of one of those cases where a product could be damaged and it looks really aggressive to this pipe wall. But when they take the measurement with the feeler gauge or whatever, they determined it's less than 10%. So this product, though it looks dramatically damaged, is actually perfectly acceptable. One thing to keep in mind is that you need to inspect this workmanship after delivery, but then after any other handling operations, because obviously if you're taking it to a pipe yard and you're storing it in racks, you've inspected it. Well, then you're moving it to the site, you're moving it to where it needs to be staged to fuse it and install it. Damage can happen during all of those periods. So it's important to check the workmanship and do these feeler gauge checks wherever you may be in question. But one other point to make about this inspection is that this guidance, this 10% scratch depth, is based on older PE pipe resins. So advances in resins have further improved the embedded safety factors that limit represented. And so we're probably, overly cautious with that 10%. It could be probably thicker than that, but this is the industry standard and we kind of stick to it.
So the pipe after this will still have a 100+ year lifespan. And if there was questions on the construction observer in general, when in doubt, cut it out. That's pretty much the motto for it. And you'll easily fuse this pipe back up in a section and be on your business in pretty quick time. So we're going to look at the fusion process inspection right here. And varies, of course, based on pipe sizes. The equipment size does scale up and become more automated as that pipe gets larger and larger. So on a smaller diameter, the worker will have more impact on the alignment of the pipe and putting it in the machine correctly. When we get to a monstrous pipe size, then the machine will line up and make sure that all of that process is done correctly with the machine. But still, the steps of the fusion and the ability to go through and making sure that you have a proper fusion need to be adhered to by the certified operator. Certifications are available in smaller diameter and larger diameter as well. So they're still teaching the essence of fusion just on a larger scale as we continue to go through that process. And here, Matt, I don't know if you want to talk to us about all the things that go into making a qualified fusion joint. It's not just the operator themselves. So
absolutely. So one of the keys takeaways from that last slide, and then heading into this slide, is that the following the process is your way of guaranteeing a good fusion. It's not the only element that goes into what we call a quality fusion joint, because obviously, as you can see from this Venn diagram, we're trying to identify the overlap that is necessary to make that quality fusion joint. That means your operator has to be trained with the latest procedure, as well as trained with the equipment that they're performing that fusion on. The equipment has to be the proper equipment sized for the pipe that you're going to go fuse, and it's going to be well maintained and qualified itself. Then on top of that, you've got a qualified procedure that you need to follow, because it's got to be a proven procedure for that product. So the section, when we talk about fusion process inspection, we're really talking about that last element, that quality control, and making sure that you're able to control the fusion process is the absolute best way that you're going to guarantee a good fusion. We'll talk more about post-fusion inspections, but in the end, if you're not following the process, you're not going to have repeatable success with fusion. So those are the key elements to making.
I know they've given me a card and they've given Pete a card. So, if we could do it, I think you guys out there in the web world can make sure that happens.
Absolutely.
As well.
Yeah. It's not so much that it's a complicated process that any good-minded worker can't do. It's just simply, it is important to follow.
Yep. When we're on the job site and we're thinking about other things, it's very important to think about the task at hand. I've seen many pipe crews out there with larger pipe that they're missing fingers, and we certainly don't want that to happen when doing any amount of work with pipe in general. So we prepare the pipe fitting and the equipment. We make sure everything is clean in that environment to lead up to a successful fusion. Electrofusion is different from butt fusion. The actual process that happens is the same. We're melting that material, allowing it to blend into the other melted section. And then the final stage after it's cooled of fusion is exactly the same in butt fusion and electrofusion. It's just the mechanism as to which that heating and cooling is taking place is what different. Butt fusion accomplishes that through having a properly prepared surface, and then heating each element together and putting under the right amount of pressure for the right time period. In electrofusion, there's coils that are embedded within the fitting that allow mixture between a hot zone and a cold zone to be able to have the final product be the same. So there are ASTM standards and procedures for you. You can see in some of these pictures what I mean by scaling up as the equipment gets gets larger, then the piece of equipment will actually take and do a lot of the alignment for you. When we get into smaller diameter service connections, as you see in the top right here, we've got a simple saddle around it, and we just properly prepare that location of the electrofusion saddle in order to be able to adhere to proper fusion principles. So properly clamped pipe is what we're looking for. Debris contaminant free. So we're looking for to be dry. So we're going to be covered from the rain or snow. If it is in the wrong temperatures for fusion, we want to make sure we make any type of temperature adjustment. If you're heating and doing butt fusion in the middle of winter in Wyoming, you're probably going to be looking for worker comfort, as well as making sure all of the equipment is stored in the appropriate temperatures that they need to be doing. So each different job site has its own challenges that you will overcome through making sure that the pipe, the equipment, and everything is in good working condition and in good environment. Yes, Pete.
Yeah.
So I would like to share with the audience that we're not going to use your name if you ask a question. That encourages more questions. Alan, I have a question and a comment. The first is there a list of certified personnel that is kept? And I'll take that one. Yeah, we kind of have, and this is from an inspector in LA, we kind of have it. But Lee, one of the reasons I talked about the distributors that sell polyethylene across the United States is because we want you to use one of those distributors. They're buying into the program and they drink the Kool-Aid, and they have qualified staff that has been trained properly. Now, do we keep a list and say, hey, here's the list? No, we don't. But if you have a project and you're working in a certain diameter range, I will make sure that there are qualified contractors to bid your work. That's part of the service I provide. Another question was, how about expiration dates based on new procedures? Those qualifications that Alan and Matt have been talking about are good for 2 years. The gas industry says just 1 year. Our industry says, hey, if you've got the card for electrofusion or butt fusion, it's good for 2 years. And Alan, briefly, if we could keep the responses to the questions down to a minute, we can get more questions today. Here's a quick one as it relates to what is the impact of debris and other environmental factors on this ASTM F2620 fusion process?
So debris or other contaminants that come through could lead to poor fusion. So we want to make sure that the interface between the two pipes is clean and free of that debris. The facing of the pipe, we're actually removing pipe material as we cut through, removes that debris and provides us with virgin resin to be able to melt and push together. After we've done that facing and we get the shavings off, we want to make sure that those are removed by a clean, dry paper towel that is free of contaminants as well. So that facing process allows us to stop those potential contamination that could lead to a poor fusion. If you have site conditions that have excessive wind or what have you, we would be looking at tenting that location to be able to keep out the environment that could otherwise lead to poor fusion itself.
And one other method involves capping the ends of the pipe, because obviously wind can blow debris into the interior of the pipe. So if you cap the ends that you're not actively fusing, you can keep out debris. And if it's a cold temperature where you've maybe put the actual fusion equipment in a heated booth or a controlled climate or protected from the rain or whatever, you are going to keep that same condition present.
Matt, would you like to walk us through this slide for the actual fusion process inspection?
Yeah. So obviously, you've taken the pipe, you've clamped it in place, you've made sure it's clean, you've faced it, you've checked alignment. Now the point is we're going to go to melt the pipe. And so for butt fusion and conventional butt fusion, you're putting a heater plate in between the two pipe ends that you're going to join. You're pressing the unmelted pipe up against it, and you're applying a specific process controlled. And of course, your heater plate has reached the appropriate temperature, which you have to check with an external thermometer to guarantee that the process is at the right temperature. You apply a bead up force and then reduce to what is known as a heat soak force. And that is the duration that you're trying to melt the pipe. That's pressure against the heating plate. Once you've achieved the appropriate melt, then you're going to pull the pipe ends off the heater plate, remove the heater plate, and then push them together. And so these key process inspection spots are things that you need to make sure are done for every single fusion. And so all of these steps, they can be recorded to create a record for your qualified process. And so the next step,
if everybody out there can see this bead that's created, this is on the inside of the pipe. It is exactly the same as the bead on the outside of the pipe. And then as an inspector, there's certain things that we're really looking for in the shape of the bead. Once this heat is created, and applied to the pipe, we also have to properly cool it down before we do any type of rough handling with it. So it's important to allow it to have the appropriate cooling mechanism or time period in order to be able to be a solid joint. So here's some of the visual inspection that we're looking for from acceptable, unacceptable, and the like on the actual bead itself. What all can this be telling us, Matt?
Yeah, so these are usually generated from your qualified procedure. And so the industry standard procedure is the ASTM F2620. And so these images, what you're looking for on the bead is really that it's uniform around its circumference and there's no specific irregularity. Then also there's that V gap that you want to make sure is above the original pipe wall dimension. And essentially you're making sure that you've applied the right pressure. So when we look at post bead inspection, visual inspection, it's really only helpful in flagging those glaring mistakes that would have been made during the fusion process. So you can have a good fusion you can have a poor fusion that looks good, but if you follow the process, you're going to have a good fusion that looks good.
So that's why we also have data recording that's here. So it actually tracks all of that process. The certified operator knows how to use this machine as well, and they attach it right to the fusion machine as we go through. It will track what the joint is, which joint by a number. It'll track the process that we outlaid for heat time and all of those other things that are necessary, and print you out a good viewpoint in that standpoint as well to track the actual joint. So
yeah, and
we'll talk more.
Good controllers also allow you to record the weather conditions, the ambient temperature, the wind speed, and the GPS location of your specific fusion as it's performed. That way you can follow back up after the fact.
Matt, I want to jump in real quick to address a comment from Resin Hutkins for the minimum bead requirements. So everything you guys mentioned, that is all standard procedure. And he referenced ASTM 2620. And at the end of the day, we always need to make sure that the fusion is actually following up and actually getting to that minimum bead requirement. So although the heat time might tell you it's 1 minute and 11 seconds, but it's also telling you need 3/16 of an inch on each side, we're going to have to wait until we get that 3/16 of an inch. So if you're working in the Pacific Northwest in the winter, you might have to wait 1 minute 45 or 1 minute 50. So that's the standard we always want to make sure we're hitting.
That's right. And that's just during bead up. So that doesn't represent that final rollback bead dimension. That is literally as it's still in contact with the heater plate.
So there are new technologies now that we are starting to incorporate within the high density polyethylene industry. If you heard me speak very much about high density polyethylene from a civil engineer outside of the industry viewpoint, I've seen a huge amount of technological development, ease of productivity tools and other things throughout the HDPE industry that makes life easier when we're installing this. And this is microwave HDPE fusion inspection. It's a new technology that essentially has a sender and a receiver on opposite sides of the pipe, and then we actually look at that joint itself. You do have to DB the exterior of the pipe in order to be able to make sure that that tool can traverse circumferentially around the pipe. And then it does look for fusion and how that molecule is actually blending together of what we're really attempting to do through the data logger, and making sure that the molecules run across each other in the crystalline and the amorphous regions themselves. So here are just some. Again, this is pretty new on the cutting edge of technology for that fusion inspection. We were looking at things that could be good fusion, hydraulic fluid contaminated fusion. So if we get to a scenario as to which some type of a contaminant was there, it's going to impact fusion process and parameter and really send up a red flag for us that it wasn't done correctly. Or if potentially water had gotten onto the actual face of the pipeline during fusion, then that water could release steam as it goes through and gets heated, and put a pocket of absence of material in there that we're looking at. In cold fusion, where we're over pressurizing the pipe and forcing it together to not allow the proper time to be able to fuse that pipe material. So this is just a new tool that's coming through, and in the next several years you'll be hearing us talk more about it as it comes in more popularity. So we'll go right straight to leak testing now. What are we inspecting? We're looking for faults in the pipe line in general, for regardless of pipe material as we go to put in its installation or its connections. Of course, high density polyethylene is a leak-free material. So if fused from one end to the other, we're not going to have any leaks. But oftentimes when you are putting in new systems, we have to connect to valves or other pipe materials, and a completely monolithic system for a municipal water wastewater system would be almost impossible to achieve in some places where we have a lot of existing pipe to go through. So one of the key things to understand and differentiate between legacy pipe and then high density polyethylene is that there are allowable leakage rates within those legacy pipe systems. And part of the way that these things are constructed is what leads to that. So what you're looking at here happens to be an open cut installation project of high density polyethylene. And as the crew moves forward and puts this pipe into place, the local MOT conditions or road resurfacing conditions may very well kick into where you'd have to bury this pipeline before we could turn it back on, in which case that's where the allowable leakage rate comes into play for legacy pipe materials. It would be extremely costly for the contractor to dig up the entire run for a little bit of leaking to be able to properly access the pipe that was installed. And that's one of the reasons why we have an allowable leakage rate as such. In suburban and urban environments, just getting across the road via traditional open cut excavation, we're limited to lane closures per night, where you're having to put in segmental pipe and then trust that when we finally connect it and make those connections, that it's not leaking. Some of the benefits of high density polyethylene would allow us to take advantage of the leak-free system. How is this different from a regulatory perspective? Those of us that have talked about it until we were blue in the face know that the commodity value is what really differentiates the municipal water and wastewater sector from a municipal gas sector or some other type of a commodity that we're talking about. So when gas mains leak, things blow up and kill people. So the consequence of failure is severe in that situation, in which they want to make sure that we know the condition of the pipe, we know when it's going to fail, and we proactively replace it. That is pushed from a regulatory perspective. In potable water, sometimes we're pennies on the dollar, if that, sub pennies, to the value of the actual non-revenue water lost. So there's not as much incentive to make sure that we replace this pipeline and fix the non-revenue water lost. So here I provided some information on the leak-free system as to what we are seeing throughout the country as averages. 355,000 million gallons per day. That's a strange way to think about water consumption, but that's a really large number that we're going. 16% of that is 56,800,000 gallons per day. Most bills are in the $4 to $5 per 1,000 gallon range of your consumption, and the average 2 to 3 bedroom house is in the 3,000 to 5,000 gallons per month, minus irrigation. So on whole, we are consuming a lot of water. And when we start to track the value of the revenue lost, we get down to the bottom and we see that a yearly non-revenue water loss could be $75.7 billion. That may seem like a big number, but for the operating budgets of many of these agencies, as to which we're continuing to repair systems as opposed to proactively replace it, that may not seem like a lot to them. So here's the ASTM Go ahead, Dan. Yes, sir.
Sorry, Alan. I think I might have jumped the gun on you a little bit early, as I see leak testing just got pulled up. And I'm not sure if you or Matt want to answer this. I know you've been on a ton of job sites in person, but they are wondering if the flex in HDPE is something that you can observe during leak testing. I'm guessing they're getting at the swelling of the pipe. I'm not too sure if you actually can see it or not.
Absolutely. So in bell and spigot pipe systems, if we do have a leak somewhere along the joint and it's already buried and we don't know about where that is, makeup water is the amount of water that we are allowed to add back into this pressurized system in order to be able to still say that we're pressurized. So that in itself is saying that, hey, we know there's a leakage rate. We know we're going to pump back water into it. A lot of polyethylene systems are fused long runs above ground and then pulled into place either through pipe bursting or horizontal directional drill. As you start in the morning and we warm up during the day, now the temperature of that pipeline will increase, and the overall body of that pipeline, the size of the pipeline, will also increase, allowing you to put more water, makeup water now, into that pipeline. That doesn't mean that the pipe is not sealed from end to end. That just means that now there's more internal volume due to the expanse size from the thermal expansion of that pipeline. In Florida, the way that we handle that is simply take pressure tests in the morning for that hour or two that we're really looking at. It's also important when you are connecting these to other systems, if we were to pressurize, we have a healthy respect for the operating system pressure as opposed to the pressure rating of the pipe. So a DR11 can be used in many municipal water systems, which has an operating pressure of 200 psi, but the operating pressure through the system itself can be in the 55 to 70 psi range. So if you turn that up to 1.5 times that 200 psi and you're connected to an existing valve or other thing, you're going to try to make sure that valve is properly secured and you're protecting the existing system as we go through.
Yeah, and Alan, that's due to the Poisson effect. Basically, as you expand the pipe during pressurization, the pipe length is going to want to contract. And so you're going to notice that you may have a pullout force that you need to account for when you transition to other piping materials. When you're going from polyethylene to polyethylene in a heat fused application, those joints are monolithic and self-restraining. So they're not going to pull out from each other.
So the overall test parameters themselves, we seal off that end of the pipe, still allow us to be able to access the inside of the pipe through an opening that you're seeing here on this fitted end. As we go through, we're going to get to that max internal pressure that we're looking for, let it sit to be able to see if we needed to add any makeup water that way, and it takes care of the expanse of the pipe material as we are charging that interior of the pipe. You reduce that pressure by 10 psi and hold for 1 hour, and then we look for any additional makeup water that goes through there. For the long runs above ground, this is a pretty robust process, as we're looking for any leaks whatsoever within the pipe, and they would certainly show themselves through this process. Again, it is very different from bell and spigot pipe when we're limited to certain sections to be installed because of MOT constraints and other things. Again, I said trenchless installations are different than traditional open cut. Here's a prime example of a segmental pipe being put in. By the time that they bury this pipe up again and realize that they can't maintain a pressure test on it, then it's going to be pretty costly to come back in and expose that pipe and do that fix. So the benefit of having high density polyethylene above ground to be pulled into place that we already know is pressure tested, and not pressure testing it after backfill and compaction, is pretty easy to observe. So here's again some differences in installing the pipeline as we move forward. Here we can see that these pipes may or may not be leaking as we install them, and we would have done the pressure test in advance of pulling these long runs into place as well. There's a process called pre-chlorination. So at the same time that you're doing that pressure testing, we're going to disinfect the interior of that pipeline. So they'll put bleach through that pipeline to be able to make sure that any contaminant that may have gotten into it is knocked out and disinfected through it. You're flush out that disinfected water and put it back with potable water from the water system, and then take 2 days of subsequent bacteriological samples that will prove that the interior of that pipeline is safe and disinfected. And then by the day of the pull for a horizontal directional drill or pipe bursting, you'll seal off the end, connect it to a swivel or other sealed end, and then be able to pull that into place. It's a rather robust system as to which we'll be able to turn that pipe on almost immediately in the states that have approved the process. But we'll look more towards installation inspection here. What are we inspecting? Construction materials, the installation methods, including handling, joining, pipe installation, new or rehabilitation, trench design, embedment. What you'll see in the bottom right here is locate balls on top of a high density polyethylene as well. So we'll oftentimes put in tracer wire and locate balls if we want to make sure that we have belts and suspenders to be able to locate this pipe in the end. In traditional open cut construction, what we're really looking for is good backfill conditions for unique burial conditions, such as excessive point loading or very deep installations, or very poor native soil conditions. So typically that 2 to 3 feet to a 25-foot depth range can be installed with no issues on high density polyethylene pipe in general. From DR11 to DR21, we're looking at specific scenarios if you want to look at pipe soil interface type. Yes, Dan.
Okay, yeah, you went on a little bit longer. I was going to ask you when point loading is a concern, because I know a few engineers were conservative and addressed that with you, and I know it's come up a few times.
So the scenarios and situations for traditional open cut excavation that we're looking at are going to be very poor soil that's a native backfill. That's a class 3, class 4 soils. Of course, we don't use a class 5 soil. Don't recommend it for many pipe types at all. And then an unconstrained or an uncompacted backfill situation makes it so our pipe stiffness component of the deflection calculations have to be larger than the soil stiffness components of those. So that's available in Plastic Pipe Institute's Polyethylene Handbook of Polyethylene Pipe, and probably more than 95% of the pipeline engineers really want to know about deflection or unrestrained calculations on the existing pipeline, but there can be unique installation conditions as to which you want to look at those calculations.
Okay, yeah, and as a mechanical guy, I know one of the interesting things that we covered a week or two ago was that the soil maps are actually listed. They're pretty well plotted out. Was that the USDA you sent me, I believe?
That's correct. US GS. They have a
USGS,
very
okay.
robust soil map network online that you can take a look at. And then also the design guidelines have, if you don't have information about your soils, conservative assumptions to make when using those calculations as well.
Awesome. Thank
Okay.
you.
These are resources available to you that are listed. We've mentioned C901, C906 before, M55, just AWWA just reissued a new version of their handbook that is easy for you to use. It's also, most of those are included in the engineers package. We're not allowed to include ASTM or AWWA standards themselves, but we do list those out so that way you can get them if you'd like to. Chapter 7 of the polyethylene handbook on PE pipe talks about all things underground installation, and it's a very good resource for you that's here in the engineers package. Here we have an installation EF hammer test. Pete, do you want to come on and tell us about this hammer test that you and Richard and Drew were able to conduct here?
Well, this is the most scientific of all the tests that we'll have in the show today, Alan. To be sure, this is our good friend Steve McDonald. He had an owner who didn't really trust electrofusion, but you know what, Alan? Electrofusion is just as good as butt fusion. In both cases, you got to follow the rules, and that's what we did when we put this pipe display together. So good work, Steve McDonald.
Thank you, Steve. There's other reassurance testing that we're going to get into talk about too. The bend back test, guided side bend test, and other things that you can accomplish on site. These aren't necessary for every fitting or every installation. Obviously, these are destructive tests that you would perform. So if you're curious about a new fitting from a new fitting manufacturer, this would be a good opportunity to try to do those to validate that the fitting does pass the testing that you're looking for. Maybe you'd want to do 1 or 2 of these tests on every start of the project to make sure that the fusion operators are following the process and the step correctly in the way that they should be following that step. If you're unfamiliar with a contractor, to go through some of these other robust tests. From that, I'm going to talk about F1055 standard, which is a joint crush test coupling preparation. So we will take and cut an actual coupler longitudinally across that coupler. This is something that you can test in the back of your pickup truck if you got a vise mounted on the back of it. So we'll have the fusion operator, the electrofusion operator, make sure that they perform the test or perform the electrofusion properly in the field. And then this will actually go through the process of forcibly smashing down that pipeline to see if the coupling crush has passed that electrofusion process or failed that electrofusion process. The Alliance for Pipe has a very good video of this that will be coming out hopefully in Q4 in some of our social media posts that you might see. But as you can see here, the coupler on the left did pass the electrofusion process here, and the one on the right, it was not prepared properly. That surface preparation is key for electrofusion. This is something that a construction inspector out in the field can do in the back of a vise in the back of a truck through here. So the same thing with a saddle can be done. As you could see through these cross sections here, we're still taking a longitudinal cross section of it. The saddle fusion parameters are exactly the same, and we're showing you what is a failed or a pass here. Actually, I don't have the fail for you, but you can imagine as that pulls away for you. Oh, yep, we got them on the next slide for you. You could see here that this was improperly prepared, and the bond did not happen correctly between the saddle and the mainline pipe. And as we go through and crush that pipe in a vise, that failure will show up right away. Again, with butt fusion and electrofusion, if the process is followed appropriately, that joint should be stronger than the pipe itself and should not be pulling out of this saddle as we show here. So this is an easy test for you to do on a relatively inexpensive fitting with a new contractor to make them show you that they can do it appropriately. So here's a FET strip coupling preparation. This one is slightly more challenging to be able to get to as far as looking at what we are trying to analyze through this. We're going to bend that strip about the fusion line and then get to our end results. Here we're going to show a proper pass of this test and then a FET fail of this test right here in this scenario. So there's multiple different ways, but these ones are all destructive in this manner. And again, some of these fittings may be appropriate to do in a destructive manner if you're trying to get to know a new fittings manufacturer or you've got a new contractor on the site doing that. And Matt, do you want to take over and talk a little bit about the data logger here?
Sure,
and what it's showing us?
So obviously, we talked about earlier all the different steps and things that you could record in real time. And so what that allows you to do is have that proof that you've followed it successfully and you're basically trying to guarantee it won't leak. It's definitely important for more sensitive or challenging installations where you've got, and I believe the next slide will go through a little bit, but essentially where you won't be able to recover and redo the work that you've done. So you're going to want that extra reassurance on the front end. And so recording all of the fusion process steps will allow you to prove that without having to go back to redo your work. So obviously you get to see that beat up pressures, that first initial spike. You've got heat force and heat soak time is that long under the green line period. And this is a pressure versus time graph. And so then you've got a key amount of time that you need to remove the heater plate and then apply your fusion pressure. And that's what that red zone is there. It's indicating that you're applying the appropriate fusion pressure. And then you're holding it in your cooling time, the blue area, for the duration that you need to. So that allows a owner to either hire somebody to analyze all of their fusions or do spot checks of all of their fusions. They can pull up every single fusion on the entire job and review the data.
So when Matt had talked about sensitive locations, what we want that high value asset where consequence of failure is severe or consequence of failure will go unnoticed for a significant amount of time. So the left here is a 54-inch, 4,100 feet low pressure force main on Miami Beach that we want every single one of those joints to be absolutely perfect. And your fusion tech is going to want that too and have the proof on it, because after this asset is installed, it could be some time if it fails to be able to discover where that failure is and then also endeavor to be able to replace that if that's the case. The same thing with the picture that you see on the right when this is simply a subaqueous or a bottom of the river type of installation where if that one was failed itself, if this pipeline was, we could be leaking some of the useful water that we're trying to collect through this as that is a source water pipeline. Yes, Pete.
Hey guys, you're doing a great job. We're running a little behind. I want to let our audience know that this webinar is planned for 15 more minutes, and there's still a lot of great content to come, and at most we'll be 5 minutes late on the end, but please stick with us and enjoy the balance of the content.
Thanks, Pete. So some of the key observations that we're looking at are disinfection procedures, pipe scraping or gouging, as we've talked about significantly earlier, proper alignment of that inspection or installation equipment, handling of the pipe beforehand. If it's offsite at a laydown yard and we want to pull it into place, either for a horizontal directional drill or pipe bursting application, that construction observer should walk the full length of that pipeline to look for gouges or scrapes that are in excess of that 10% limit that we're talking about. Want to make sure that that tracer wire is continuous. So for a sensitive pull through high friction areas, we may very well want to do a beefed up tracer wire or 3 to make sure that we have that asset to be locatable in the future, and all proper compaction backfill are necessary. We talked about when in doubt, cut it out. This picture that you see here occurred a 3:30 a.m. on a pipe bursting project that was on a DOT road where we had very minimal time for road closures. That was from 7 p.m. to 5 a.m. And I had noticed a very large gouge in the pipe. Second pipe run that they were pulling into place on the second night of the actual pipe bursting process. And all it took for the superintendent on the job site, after I had determined we were cutting that section out, was to cut out a 5-foot section that contained the gouge, and then to be able to butt fuse that pipe through. And they lost about 25 minutes. So when in doubt, cut it out is exactly what I go by. And here's some process of how that happened. Oftentimes we use truck tires or other things that are soft to directionalize a pipe moving process from the laydown yard to the installation location. Here you see a piece of plywood that's up against a dumpster. The second night when they had the gouge, someone forgot to put the plywood in, and so the edge of the dumpster then gouged the pipe. These are normal scrapes that are okay. This is on the right. You see just a bead that's scraped through, and they pull that along the ground for pretty typical processes. And this does not exceed the 10%. If you don't want that, there are rollers and other things that they can pull along. This is the gouge section in particular that I had wanted to have cut out. So I did have doubts about this and did believe that it exceeded the 8-inch DR11 wall thickness beyond that 10%. And we simply cut it out as we go through. So we want to look at locating mechanisms. Of course, high-density polyethylene is a thermoplastic material that is not electrically conducive, not like a metallic pipe. So we want to often put that tracer wire, float balls on that. Sometimes the guys in the field can get pretty creative as to how they connect these to swivels and other things to make sure that they make it through. So the picture on the left, you'll see that this is a stainless steel tracer wire that they have taken out of its plastic wrapper and then braided in amongst itself after they've put it through the swivel through here. So that's a very heavy duty way to connect it. They did pull multiple tracer wires through that. On the picture on the right, you'll see as well, wrapping around the screws that actually screw into the high density polyethylene head through the expander head in a pipe bursting operation. Some things that we're looking at post installation: CCTV to validate line and grade for gravity sewer application or storm sewer application. Smoke testing, we can smoke test polyethylene pipe for gravity sewers themselves, or low pressure gravity sewer testing through that as well. We could, and then preparation of those as-built documents in whatever manner that you want to, as an engineer, collect that information. So there's lots of different mechanisms to be able to provide those as-builts. If you have GIS records that need to be beefed up, it is quite possible to use a Trimble or other GPS locating mechanism to actually get on top of any of the valves or other important appurtenances that you want to capture their location themselves. So we're going to talk about fusion qualification. So we talked about the process inspection before and did talk a fair amount about actual qualification through that process discussion, and then manufacturing QA/QC. Pete, you got something for us?
Yeah, something quick, Alan. I don't want to push you back any further, but I got a question about once tracer wire breaks, how do I reconnect it? And does it really break very often?
That's a great question. Oftentimes it'll depend on the friction through the soils, and yes, it can break. That's why in HDD, where we have a deep crossing, we're going to put 2 or 3 of the tracer wires through there, and the same thing with pipe bursting when there's high friction forces. The way to reconnect it then, depending upon where that tracer wire actually broke, you would perform an excavation, get down and splice it together with a new tracer wire and connect it to the valve, and finally all the way up to a meter as we go through, so there's continuity through that line itself. It is not uncommon for locators to be able to try to get signal in different places. In one of the projects that I've been to, the tracer wire popped in the last 5 feet and yet they were still able to trace that line all the way up to 5 feet from where they started the next set of tracer wire on the valve to go through there. So they do have different mechanisms in order to be able to try to find this pipeline afterwards if that tracer wire does break on you. So great question. Okay, fusion qualification, Matt, you want to take some of this?
Certainly. So fusion qualifications represented in both our material and product qualifications, but it's also utilized in pre-construction on-site considerations. So, what are we inspecting? Well, the procedure is qualified and that the operator is trained and proficient with the equipment. So what is that going to accomplish? It's going to verify that the operator has the appropriate amount of training with the appropriate equipment to do the task. So next slide. So we look back at the same chart, Venn diagram that we had before, regarding the things that must overlap. And obviously qualification is a matter of 3 of those 4 elements. You've got a qualified procedure, qualified operator, and qualified equipment. Next slide. So, so looking at most of your customers, most of your manufacturers are going to manufacture their products to industry recognized heat fusion procedures. So the most common one is ASTM F2620. It's a generic fusion procedure that came from PPI's TR33 and 41 testing. And so if you're using a qualified procedure, in order to qualify that procedure, you have to do a barrage of physical tests. So for stealing again from the gas distribution industry, the Code of Federal Regulations has a very specific list of required physical testing that you have to perform as a manufacturer of the product or the utility utilizing those products to make sure that the polyethylene that you're installing and the fusion procedure that you're using are qualified. Next slide.
So we're getting into the parts of the presentation now that really builds before we even bring the material out into the field. So there are lots of things that govern safe working with this, safe manufacturing, robust manufacturing to where we say it's 100-year lifespan. It's going to be 100-year lifespan through that. And then these are all the steps and processes to make sure that when you do put that pipe into the ground, that these are the best ways to achieve that maximum lifespan that we're preaching and looking for.
And a number of the tests that you can do for actual operator qualification can be done on site to kind of reassure. We talked about reassurance testing, on-site reassurance testing before. Many of these same techniques can be used and are used on job sites to make sure that, hey, this crew that may have gotten their qualification a year ago is still up to snuff and they're still able to perform it. And more specifically with the specific equipment at the specific job site. So when you know that you've got a qualified procedure, the next logical step is look into what causes a faulty fusion. And so there's an ASTM standard that dictates the training that an operator has to qualify in order to be qualified to perform fusions. So F3190 will require physical tests of samples that they make in order to receive your qualification card. So next test. So the most common method is actually found in F2620. It's the bend back test. Basically for 1 inch and thinner pipe walls, you take a longitudinal test strap from a pipe fusion and then bend it back. So the inside of the pipe is on the outside of the bend and the outside of the pipe is on the interior of the bend. And so basically you're looking for that bond continuity and to justify the strength. So you can't see any cracking or crazing or any sign of failure. And of course, these ends are bent all the way back to touch themselves. So it's a very rigorous test on that actual fusion.
So Matt, with a wall thickness, let's say it's a 24-inch, 1 inch wall thickness here, you're probably not going to bend that back by hand, right? You're Incredible Hulk probably could if we were watching the Avengers, but not gonna be able to bend that one back by hand. That's a pretty stout, robust.
Right. Yeah. 1 inch is
thing,
really the limit of this test. But yeah, you can put it in a vise and then just bend it over on the vise. And so
Can we
here's
do
what
that?
not to do.
Ah,
Yeah, if you've got a bucket out in the field, this could definitely potentially kill somebody if that were to fling off in any direction as you're trying to bend it back.
so here is what we actually do. They do make production equipment for you to be able to handle this. It is a test that you can do to test new fusion equipment, new fusion operators at the start of your process, in the middle of your process. If you just want to go through some further QA QC, what we'd be seeing is pass tests, looks like in the middle there, and then maybe a fail test, what we see on the right here. Is that about right, Matt?
Yep,
We're looking
sums
for
it up
that.
perfectly. And you can do this in the field because all it takes is a saw, a planer, and some measuring calipers to conduct it. So it's definitely something that you can do on a job site as an operator qualification or reassurance for your pipe install.
Just because the Alliance for PE Pipe has a big Penske truck and hauls all this stuff around doesn't mean that everybody out there can't have their own equipment to be able to do so, to make that happen too.
Definitely.
So we'll talk more about manufacturing QA QC through here. And this is, I'm going to demur to Matt because this is much more his realm than mine, but I still will frame the important components of it as it applies to field inspection. We only have about 4 minutes left of the regular time, Matt. So high step it through these.
Yeah. So making solid wall DR pipe is a multi-step process. You got raw pellets that extrude through a die into a vacuum tank to set an OD, and then it comes off the extrusion line and cut lengths. So what are we trying to test? Go to the next slide. We're testing on site raw material properties. We're testing the dimensions, the workmanship of the product as it comes off the extrusion line, and we're performing physical pipe property tests. We have to set out that the resin we use, the product that comes off the production line, and the pipe itself can withstand the environment that you're about to put it in for 100 to 50 to 100 plus years. So next slide. So before we get into those kind of tests that we do, we want to look at, where do you get your guidance from? Well, the Municipal Advisory Board of PPI, they're a team of experts that offers advice on the industry. And so they've drafted a specification for potable water applications of HDPE. And go to the next slide. Basically, this specification is going to outline all of the material properties that we require people to make and produce our pipe to meet. And so that's PE 4710s, it's a 445574C cell classification. But probably more importantly is that the manufacturer has to have a listing in PPI's TR4 that says they've done their data to make sure that their products can meet the pressure rating requirements of the product. As well as the next part would be AWWA C906 is a required standard to follow for any potable water application. And
so if
that's
I wanted to manufacture high density polyethylene, Matt, I just don't go in the backyard and start to push it through into a homemade job right over here.
That listing that you're going to see in TR4, it's going to take a minimum of 10,000 hours of sustained pressure testing of numerous samples. I think it's over 100 samples, something like that, on pressure test for 10,000 hours. That's almost 2 years, I think it is.
Your facilities get randomly inspected too, don't they, Matt?
Absolutely. So they're audited, and as a PPI member, you have to continually renew testing of your products. And so most of that is controlled by the resin manufacturers that we get our supply from, but it's our duty to make sure that listing continues to be met. And so the next bit is we need to physically test the product. So C906 requires like daily tests of bend back or elongation to break. And basically these two tests, you're really trying to root out any flaws in the resin or extradite quality. And so you're focusing, this bend back is basically taking an arc of pipe and bending it so the inside of the pipe is to the outside. And if you have no stress marks, no cracking, crazing, or fracture on the interior of the pipe, you're not going to have flaws that have manifested themselves in this test.
I know Pete's pretty excited about us blowing some stuff up, so I'm going to go ahead and get us through to some of these that blow up. And this is called a quick burst test, is it not?
Yeah, that it is. And it's the highlight of the plant tour. So basically this pipe that's rated to 335 PSI is going to be pressurized up nearly 4 times its pressure rating. And as you can see, it expanded as it approached really close to, I forget what the final dimensions, nearly 1307 PSI, I believe it was. So the purpose of this is that you're checking the reserve strength of polyethylene. You're making sure that it's a ductile failure. And that's highly important because polyethylene in its typical operating conditions should be in the ductile condition. So if you have any sort of fracture failure that you would see if you conducted the same test, maybe against a PVC or a ductile iron product, you would possibly see a brittle failure, which could result in long fractured series of pipe that's very dangerous in the field.
And this test is another test within F1055 that looks at the actual electrofusion joint integrity. And we've got a saddle drop test here that shows forcibly trying to break this fitting off of this pipe. And you those in the audience are not a luxury to see it, but the failure, there it is, did not occur at the pipe wall itself. When we're looking for this test. So that's one of the things we're looking for, proper fusion.
Well, actually, it did occur at the pipe wall, not at the fusion. So it actually tore the saddle away from the pipe wall.
Which is what you're looking for to say that your fusion was good. It must break the pipe itself, not the fitting.
And then the next one after this is a crush test where we're looking at deformation of the pipeline.
And you're trying to root out knit lines that may happen in an injection molded fitting like this. And as you can see, this thing almost returns to its normal shape. Over time and pressure added, it probably would return to its normal shape, but it just illustrates the robustness of polyethylene.
It does not deform, so it's not pushing or changing coloration, rather. So it's not pushing past its deformation limits there. And Matt is correct. We easily could come back to its nature. Dan Landy, have you seen one of these before, this EF coupler test here in person?
I have. It did not blow the cover off in the same fashion. It wasn't that explosive, but yeah.
Yeah, so what we were doing there is we were testing a 10-inch coupler that I had made, and we were looking for that deformation that, next slide please, that Matt was talking about, and this is what that looked like. So the pipe wall failed, not the electrofusion coupler. So this is a test that can be done. This is a ASTM standard as well. Hey guys, let's wrap things up. I want to say thank you to you guys for doing a great job. Matt Hahn and Alan Ambler. Good work. This is how you can reach these two fellas. And then Dan Landy is going to be your resource for the engineer's package, CEUs, and any other questions you have. I only have 2, 4, 6, 8, 9 people that have asked for a PDH or CEU. Please send Dan your requests. And also, Dan and I want to be very involved in your next polyethylene project. So send us a little information and let us know what's going on and how we can help you. Matt Hahn, great job today.
Appreciate it.
Alan Ambler, good work. Look forward to seeing you on this location again soon. Dan, thank you very much. And our audience, great job today. We kept everybody all the way until the end except maybe 15 people. So good job. We'll see you soon. And don't remember, fuse it or lose it. Thank you very much. Till next time.